Good morning, good afternoon, or good evening to everyone today for this webinar. We would like to thank our invited speakers, the EAGE technical community on geomechanics, for organizing this event, and also all of you for being here. We hope you enjoyed the session and learn a lot, and with that, we will begin the webinar. Anke, I hand it over to you.
Thank you so much. Yeah, I repeat, good morning, good day, good evening to everybody who joins this webinar. So this is webinar number 2 related to our expert dialogue. So we will have 3 presentations followed by a panel discussion. So you can basically ask questions or make comments. The chat is open and you can use it throughout the entire 3 presentations. We will have the panel discussion at the end of presentation number 3. Topic of today is hydraulic fracture stimulation in tight rocks. We have 3 speakers. Welcome. Very nice that you joined us. Ding Chu from Texas A&M University, Garrett Fowler, ResFrac, and Liu Hai from SLB. And I'm Anke Simone Wendt, together with Peter Achtiger, who is now smiling. We are co-chairing and chairing this geomechanics community on behalf of the EAGE. Just go to next slide. So the EAGE has accepted our petition to create a brand new geomechanics community last year. So we are extremely pleased. We are a small committee, 10, 12 people, who put this all into place, and we announced the geomechanics community last year at the IGS for the first time. Then over the winter until end of January, we made some plans on what we would like to do for you, for the community, and we rolled out the plan and published this both on LinkedIn and the EAGE website. So if you go there to communities, you can see what we are doing in terms of geomechanics activities. So we have the expert dialogue. We invite you to participate in webinars. So you can say, I want to present a topic. We have theater sessions at the EAGE annual. We will go also to Get with a special session that we are currently preparing. So plenty of things. And actually, I should also mention in the EAGE annual, we have a special session also for young geoscientists. So we already have seen how our afternoon will be structured. So we just jump a little bit more into what do we want to do on behalf of the community and beyond the activities. So most importantly, we thought we want to bring together inside EAGE all the geosciences and the engineering, inside the geomechanics domain. And with this, we want to foster knowledge exchange, student engagement. Of course, we want to look at the subsurface as an energy provider, the subsurface for storage and disposal. Many of the topics we are discussing are related to energy transition, and we are not excluding tunneling and mining. We have currently, actually, the community is growing very fast. I think we have nearly 750 members, so basically since November last year. At the Geomechanics Committee, I said we are a number of people. Here's a list. You find our list and actually our respective responsibilities on LinkedIn, but also on the EAGE website. So if you would like to contribute and you have something very specific, just look at one of us and contact us, probably easiest through LinkedIn. Thank you. Community activities, as I said already, is EAGE Annual, the GET, and then we have networking events, collaborations. And of course, if you want to post on our LinkedIn page any sort of comments, news, career advices, you're very welcome to do so. We always share our information via the LinkedIn page. There are very regular updates related to EAGE, but of course also very specifically to our community. EAGE Annual, so we are hoping you're coming because we will be there. Then GET, we will also be there with a special session, and our special session will actually focus on geothermal. That's what we have decided a couple of weeks ago. And here's our community. So if you want to join, it's completely free of charge. You can just go to LinkedIn, use here the picture to access the LinkedIn page. Or if you don't have access to LinkedIn, you can just go to the EAGE organization page and then communities, and you will have the chance to find us straight away. Thank you for joining today, and I like to introduce our speakers in the order of speakers. So we made a little bit of a logical order. We start with an overview on unconventionals, basically challenges, uncertainties, and the path to better decisions. It will be Liu Hai who is going to present. Liu Hai is a veteran working for many years in SLB, and his primary area of expertise is in reservoir production and stimulation. Not going to read the text. You will be able to read the text in the recording, which is made available as I think on the YouTube channel of the EAGE organization. This is then followed by how are we actually doing the modeling. And we have Garrett Fowler from ResFrac who presents on connecting measurement to outcomes. And in the end, it will be the fiber optic sensor monitoring and interpretation of fracture diagnosis and well performance by Professor Ding Xu. So with this, I like to basically hand over to Liu Hai, and please enjoy the session of this afternoon. You want to share your screen, please?
Yeah, good morning, good afternoon, so everyone. Thanks for joining. So let me go ahead and share my screen. Okay, let me know if you can see everything okay.
Yes.
Thank God. Okay, very good. Today, I would like to discuss hydraulic fracturing in unconventional reservoirs, not only the fundamentals, but more importantly, why achieving consistent performance remains a major challenge today. As we all know, unconventional development has transformed the industry over the last 2 decades. But despite enormous progress in drilling efficiency, completion designs, and pumping capability, we still see a significant gap between designed stimulation performance with actual. So in this presentation, I'll walk through the fundamentals of hydraulic fracturing just to bring everybody on the same page, and why unconventional remain extremely challenging, and also the role of geomechanics, as well as why many fractures clusters are still ineffective, and why surveillance monitoring and integrated modeling are becoming increasingly important. So let me start with a quick overview of hydraulic fracturing fundamentals, because probably not everyone is familiar with this hydraulic fracturing. So hydraulic fracturing is a stimulation process where the fluids are injected at pressures exceeding the rock breakdown pressure and create conductive fractures in the reservoir. And these fractures are then propped open using proppant to provide flow pathways for hydrocarbons. So if you listen to this clearly, so basically the process typically involves, firstly perforating the casing and pumping the pad fluids to initiate the fractures, and followed by a slurry containing the propellant, and finally placing sufficient propellant to maintain the conductivity after the fracture closes. So hydraulic fracturing is particularly important in unconventional reservoirs because permeability is extremely low. Without stimulation, commercial production would simply not be possible. So now, if you look at these slides, fracture geometry, meaning fracture height, length, width, and complexity as well, is controlled by many factors here. So I'm not going to read all this, list on the left-hand side. So basically, from petrophysics to a lot of geomechanics, nature factors, as well as many treatment, conditions as well. But this is where things become very difficult. As you can see, with all these factors involved, hydraulic fracturing modeling is full of uncertainties. Just give you one simple example. So if mechanic earth model is inaccurate, fracture height prediction will be wrong. And when the fracture height is wrong, and then fracture length and width predictions will also become inaccurate. So even though fracture simulators are extremely powerful today, their outputs are only as good as a subsurface understanding behind them. So this uncertainty becomes much more severe in unconventional reservoirs. So let's now look at what is actually happening in unconventional developments today. In an ideal world, we would fracture every cluster and keep them all propped open and connect every fracture from tip to wellbore. But reality is very different. So as you can see the middle column graph there, production logging consistently shows that roughly 20 to 30% perforation clusters are not contributing to production. And more recently, perforation erosion analysis and fiber optic monitoring have shown that up to 30% of clusters may not even receive effective treatment during pumping. At the same time, normalized production per well, as shown on the right-hand side of the graph, has declined over the past 5 years, despite longer laterals, longer treatment, larger treatment, and also aggressive completion designs. You can see examples here from both Permian and Vaca Muerta, but I can guarantee you this trend is broadly consistent across all US land basins. So in a simple word, despite more stages, more clusters, and more propellant, we're not necessarily getting proportionally better production outcomes. And this raises a very important question. Are we truly understanding how fractures are propagating and interacting with the reservoirs or not? To explain this further, so let's look at the industry survey conducted globally across unconventional and international frac operations, and the results are quite revealing. So roughly 1/3 of unconventional frac jobs in North America were considered underperforming relative to expectations, and internationally about 1 in 5 frac jobs did not meet target. So traditionally, when wells underperforming, and operators may blame frac designs, fluids, propellant, or even sometimes execution. And of course, service companies may point towards reservoir quality issues. But both perspectives can be correct. But one thing that has missed, which is the number one reason here, or real reason here, is failure to fully understand the subsurface. So this explains the question, how can we really, utilize our subsurface understanding, particularly geomechanics, as well as the modeling, to really help us to really improve this performance, overall in both North America and as well as internationally. So, and the reason this is so difficult is because unconventional reservoirs are extremely heterogeneous. And shells are heterogeneous at every single scale, as shown in these slides, where, from thin sections to SEM images, to cores, to logs, and to the outcrops as well. So as you can see, this variability exists everywhere. And importantly, variability exists not only between wells, but also between the stages and even between clusters within the same stage. So therefore, mechanical properties, stresses, TOC, minerals, nature factors, and laminations can all vary significantly along the same lateral. So the question becomes, why are we still treating every cluster and every stage exactly the same way? So on the other hand, not all organic shells are created equal. If you look at the summary on this slide, North America shells generally developed in relatively relaxed tectonic environments. As a result, structures are often simpler, stress regimes are more predictable, and fracture gradients are moderate. But if you move to international organic shells, they're very different. Many occurs in a tectonically stressed environment with complex fault systems, nature factors, and many cases are stack sleep stress regimes and a very narrow stress window to overburden. And the picture on the right-hand side from Wakamata is illustrating this very well. So in addition to nature factors, while, which is a benefit for reservoir contact, but it can also significantly complicate the stimulation treatment, which will increase leak off, create fracture complexity, and reduce effective proppant placement as well. Another important feature here often observed is, particularly in Middle East, is laminations. And these interfaces can strongly influence fracture propagation. And all these factors increase uncertainty in both fracture execution and fracture modeling as well. So once we recognize this level of heterogeneity, and we start to see why even well placement itself becomes a stimulation challenge. Traditionally, drillers focus on staying within the reservoir, maximizing drilling efficiency, and minimizing well tortuosity. But where the lateral lands vertically within the reservoir also matters greatly for stimulation. The example shows here is a well that remained inside the reservoir across, vertically from top to bottom. But however, if you look at the microseismic mapping, results that, shows that some fractures growing out of the zone, and while others fail to connect all the reservoir units. This resulted, poorer than expected production. So therefore, lateral placement should not only consider geology and reservoir quality, but also need to take into account the anticipated fracture geometry and the stimulation effectiveness as well. The next challenge is the stage and cluster design. In many unconventional development today, completion design prioritize on operational efficiency, which we typically use geometrical spacing, standardized designs, and also repeatability as well. But reservoir and geomechanical properties vary significantly along the lateral. In this example, the production logging revealed that only 64% stages were effectively contributing to production, and that means large sections of laterals were understimulated or ineffective. And this highlights the importance of integrating reservoir quality, stress variations, and geomechanics directly into completion design and stage placement. Let's take this further. If we overlay stress measurements across clusters in the same stage, we often observe very large stress differences. In this example, you can see that more than 75% of stages show stress variation greater than 0.1 psi per foot. If you take 10,000 feet TVD as a reference, that corresponds to more than 1,000 psi difference between the clusters within the same stage. And that is really significant. And under this station, should we really expect uniform fluid distribution across all clusters or not? And of course not. Fluid naturally enters the path of least resistance, and leading highly uneven fluid and proppant distribution across the perforation clusters. And this leads directly to what we observe in the field. More than 20% clusters in this example often receive ineffective treatment. This explains why uneven production contribution, inefficient proppant placement, and declining the stimulation efficiency as well. But importantly, this also represents a huge opportunity. If we can improve the cluster efficiency and ensure more uniform treatment distribution, production performance could improve significantly without necessarily pumping more sand and more fluids. But to improve the cluster efficiency, we first need visibility into what is actually happening during stimulation. This is exactly where surveillance technologies become critical. The complexity also becomes even more greater once we move into infield development, which introduces another major challenge, which is frackates. As the child wells are stimulated near depleted parent wells, fractures can communicate with existing fracture networks. This creates multiple problems: increased operational risk, inefficient fluid placement, and pressure interference, and a lower production efficiency. And in many cases, we continue pumping full completion designs, even though part of the treatment may simply enter existing depleted fracture networks. So an important question becomes, can surveillance and predictive modeling help us to identify where stimulation effectiveness will be limited before we pump the job? And then another challenge, which is particularly related to tectonically stressed areas, and in these kind of situations, stimulation can also create severe completion integrity issues. Casing deformation has been reported in multiple international shale developments, including Vaca Muerta, China's Sichuan Basin, and Saudi Arabia as well. And these failures are often associated with bedding plane sleep and shear reactivation, and the stress transfer away from the treated stages to the hill sections. When the casing deformation occurs, and obviously there's no choices but skipping a lot of stages, and also many times the bridge plugs milling could be problematic, and ultimately it will significantly impact on the wall economics. This again highlights the importance of geomechanical understanding, monitoring, and predictive modeling. Another important challenge is impact of laminations. We all know that organic shells are laminated across all scales. And historically, these features are difficult to characterize using conventional logging and geomechanical workflows. But with latest high-resolution measurements, we now better understand their influence on fracture propagation. And these laminated interfaces can arrest fracture height growth, showing on these slides, and also can create pinch points and also reduce vertical connectivity after the treatment. And this has major implications for both stimulation effectiveness and fracture modeling accuracy as well. The last challenge I would like to emphasize is about doing optimized stimulation designs based on reservoir conditions to get better production outcomes. It is very common practice today to do so-called cookie cutter design in an effort to drive efficiency and reduce cost. And when a stimulated well doesn't produce, it's often blamed on reservoir quality. So let me show you a real example here from Asia, where post-stimulation performance from a campaign of stimulated wells was compared. And there's a huge spectrum as shown on this graph here in the middle, 3-year cumulative production ranging from over 3 BCF to only 200 million SCF, total. If this is all caused by variations in reservoir quality as measured by EAGE, we should expect a linear trend after we normalize production to reservoir quality. However, if you look at the bottom graph, a large number of wells were underperforming and below the trend line, shown by the red cross of that chart, and these wells are definitely not stimulated optimally. So therefore, to get the best production outcomes, we need to design every stimulation job based on reservoir conditions. Obviously, how do we solve all these challenges? And historically, the industry moved towards these complex workflows as shown on this graph that introduces more logs, more measurements, more diagnostics, and more interpretations. And these workflows aim to optimize reservoir quality and combine that with the completion quality, and then look at the where to stage the well and where to perfect the clusters, and then to increase the stimulation effectiveness. And importantly, if you look at past publications by applying these workflows, they did provide value. We consistently proving that better measurements absolutely lead to better decisions. But there was a problem. These workflows became difficult to sustain operationally. And unconventional development, as we all know today, is driven by speed, efficiency, and cost reduction. And additional wireline runs, complex data integrations, and long interpretation and the fact optimization cycles often do not fit the pad development timelines. So the industry shifted towards to simplified workflows, which is more stages, more clusters, and more proppant. But as we discussed earlier, simply increasing completion intensity does not necessarily solve the underlying subsurface challenges. And this is why the industry increasingly needs the disruptive technologies that can provide better measurements without adding operational complexity, additional rig time, and significant cost. And obviously, cost-effective monitoring and surveillance to calibrate our understanding, as well as simplified modeling and optimization workflows that fit into operational efficiency. And this slide shows an integrated stimulation value chain. And as I always emphasize, it must start long before pumping begins. It should start before drilling, and then move to look at well placement, and then formation evaluation, and then look at completion design, and then into treatment execution and real-time monitoring and optimization, and finally continues through post-treatment surveillance and evaluations. And this is where monitoring, diagnostics, and digital modeling become crucial. And they allow us to validate assumptions, calibrate models, and improve execution, and ultimately reduce uncertainty. And this directly connects to the next presentations, where we will discuss how fiber optic monitoring and fact modeling can help the industry better understand fracture behavior in reality. So to summarize, there remains a huge opportunity to improve stimulation outcomes in unconventional reservoirs, and reservoir heterogeneity and geomechanical complexity are major drivers of stimulation uncertainty. And better integration of subsurface data into stimulation design leads to better production performance. And finally, digital tools and monitoring technologies and calibrated modeling workflows are becoming crucial for delivering efficiency, consistency, and actionable insight. And ultimately, the future of unconventional stimulation is not simply about pumping more sand and fluid, it's about understanding the reservoir better and measuring what actually happens during the stimulation, and continuously improving our models through surveillance and calibration. With that, let me pass to the next presenter, Dr. Dingzhu.
Well, I'm not Dr. Zhu, but I believe I'm next in the agenda here. But that was a great intro, Leo, to some of what I want to speak about. So let's see if the sharing here all works. Someone confirm that my screen is showing up as intended.
Yes.
Presume, yes, Leo or Anka, can you?
Yes, works fine.
Showing up?
Yes, we can see your screen.
Yeah.
Okay, great.
Yeah.
All right. So what I want to do was build upon what Leo was talking through of some of the challenges in these unconventional assets, and the goal with modeling is that we are going to be creating a digital twin of the subsurface to explore why do some wells fall off that trajectory even when normalizing for geologic quality. And so what I want to walk through today is why model, some examples of how those have been applied, focusing on how diagnostics help constrain and make these models more applicable to these challenges that we face. And that will then be a lead-in for Dr. Zhu to speak through some of the evolutions and advancements in fiber optic technology today. So we saw a little bit of this from the last presentation, but the power of a model is it provides this physics-based framework for decision-making, as well as the visual intuition of the subsurface. So on the left-hand side of this slide, I'm just showing very simplistic images here of a sensitivity of changing the spacing between these wells. So each of these is a horizontal well. We can see fractures propagating. We're just modeling one stage of each, as well as the job size. How much fluid and proppant are we pumping? And and then the color scale here is the pressure depletion happening in the matrix. So what we can observe is if we do a small volume of fluid and proppant as well as wide well spacing, we have this leftover reservoir in between. If we have tight well spacing and pump a really large frac, what we likely end up with is too much communication between wells, too much overlap. We've overcapitalized that volume of rock. And so what a model allows us to do is to balance those competing processes of what is the interplay between this well spacing and the amount that we're pumping. And we can use those then to evaluate and systematically evolve through a design process. So two quick examples of the applicability of models to really impact the bottom line of these assets. On the left, I'm showing a paper that I wrote several years ago with Hess when they were in the delineation phase of their Marcellus development, which is a gas shale in the Northeast United States. And the question was on how might you change cluster spacing as well as well spacing and a number of other parameters given certain in situ permeability assumptions. And permeability is one of those things that's inherently difficult to measure through something like a logging technology, right? So we want core, but crust rock core is inconsistent in terms of the derived permeabilities. So we try to do things like in situ defit or a full core analysis, but those permeability tests are going to be more expensive and time consuming. And so leading up to that development, we looked at what would the optimal cluster spacing be with two different permeability assumptions, either of which could be validated by some of the initial data collection. And so if we had a higher permeability assumption, it was about 1 microdarcy, we would arrive at a economically optimal cluster spacing of about 75 feet. That would also imply then a much more constrained fracture area around the wellbore produced area, at least. Alternatively, if we were in the realm of nanodarcies, I think this was about 60 nanodarcies, we would end up with an optimal cluster spacing of about 25 feet. And the difference here would be about 30% in terms of the MPV on a per well basis. And so first off, that motivated, well, one, permeability was something really important to hone in on and understand in these assets of that's going to move how we design the wells. And Hess was able to go out and verify the lower permeability estimate and did so through well interference testing, right? So just from a energy balance standpoint and mass balance, if you have the high permeability and you know the production rate, that means that you're producing from a much smaller fracture area, and you would not see communication between wells at the distances they were seeing communication. So we were able to validate this lower permeability assumption. That has been consistently corroborated through the Marcellus in the years since. And that tells us that we should be designing these wells with something like a 25-foot cluster spacing at a $3 per MCF gas price. Another important component, which I'll touch at the very end, is as that commodity changes, your optimal design should change as well. That's another utility of a model. The example on the right comes from the Bakken, which is an oil shale in the northern United States, north central. And here we look at how does the optimal outcome evolve as a function of stage length and cluster spacing, as well as the color scale here is the size of the stimulation in terms of proppant and fluid volume. So measured on like a pounds per foot basis, or pounds per cluster in the case of how we evaluated in this paper. And we see that one, there is a meaningful difference between what their standard design was at the beginning of the study to 6 months later after optimizing. As well as a change, we can see the change in optimal stage length depending on what the volume that you're pumping. And notably here, there's an optimal in both cluster spacing or stage length, as well as proppant loading. So you see that the top MPV is achieved with this pink or red halo, not the black dots. So we're saying we want to increase, and then we start to see a decrease in MPV when we increase those volumes too much. So again, this is the utility of a finely calibrated model. We can use it as this framework to iterate through designs and hone in on what is going to be most economically beneficial for the custodian of those assets. It all hinges on, can we trust the model? How do we make a robust model? And in the abstract, I pulled out the quote that we're all familiar with, which is all models are wrong, but some are useful. And so that comes to the model calibration and modeling workflow. How do we trust these models? How do we gain confidence in the models and make sure that we're asking the right questions? And I'm going to focus here on the model calibration phase. And in particular, the relation of model calibration to the diagnostics available. And what we want to do is integrate the diagnostics available to us, fiber optics, which Dr. Zhu will speak to, interference testing, defits, which I mentioned, microseismic perforation imaging, downhole pressure gauges, et cetera. We have this inventory of diagnostics, and that's really exploded over the last 5 to 10 years. Is service companies like SLB are doing great things in terms of the technologies available downhole to monitor and diagnose. And we can now integrate those into models as constraints to make sure that our model is consistent with reality. So I'm going to go through 3 examples of that and how it increases the fidelity of models. The first example is one of the best field experiments that I think has been implemented in our industry. This again comes from the Bakken. It was a Exxon well site that they have subsequently published several papers on. And so the premise is that they have this primary well, their producer P1, which is a 10,000-foot horizontal well. And then they drilled 2 dedicated observation wells. Observation M1 is in the same horizontal plane as P1, but it's drilled at an oblique angle. So the toes here are about 100 feet apart, and the heels of the horizontals are over 1,000 feet apart. Similarly, monitor well M2 is in the same vertical plane as P1, but the toes are about 10 feet, 20 feet apart, and the heels are 400 plus feet apart. Then in both M1 and M2, they installed a series of pressure gauges across the laterals and cemented those in. So the idea is that as we fracture P1, we can watch the fractures cross, and we'll see pressure blips, of course, as that high pressure fracture is crossing the observation well. And then in addition, when we go to produce P1, we can assess at what distance and which gauges in those offset monitor wells start depleting. So this is about as detailed as we can get, because we get both horizontal and vertical constraint on what that depletion looks like, the consistency of depletion, the uniformity of depletion. And that's what I'm showing here on the right-hand slide. So on each of these plots, the x-axis is the distance, the horizontal distance from this producer well. So the left-hand side here would be the gauges in the toes of the monitor well. And as we go towards the right-hand side of this axis, you're progressively going toward the heel. What we see is that the drawdown, or the pressure, is lowest when the gauges are closest to our production well. And then we progressively get to higher pressures as that distance extends between the wells. Notably, there's a point where we see the first derivative becomes unsmooth, the second derivative, right? So there is a step change here corresponding to about where these red dots are. That's interpreted as kind of the extent of the propped region where we're getting the most depletion. And then once you go beyond that effectively propped region, we see very little pressure depletion. And then each of these panes steps through time so that we can see the evolution, and where you might get a little depletion out at this point in the first 6 months, we see that point is not changing through time, whereas these other points continue to come down. So this provides, again, a very detailed subsurface data set of how is this system working. And then what allows us to do is build models that are constrained to replicate this data. So that's what these points are. The blue, orange, green, red, purple, and brown points is model the pressures in a model that are at that distance away from the monitor well, so that we can ensure that our model is then replicating this pressure distribution as measured in the subsurface. So what does that look like? Here's a picture of that model. You see modeling multiple stages across the lateral here. We have variable fracture geometries. We have that pressure depletion happening at different distances. And this background color, we see we have the most pressure depletion closest to the wellbore, and then we progressively get less. And then there's a border or threshold here after which we see very little depletion. And if we look at a profile view of a single frac, we're showing fracture conductivity. So we have this region of high conductivity around the wellbore, and then we progressively get less conductivity as we extend far away from that treated well. So In this paper published by a colleague of mine, we're able to calibrate to and constrain our models to that pressure profile, both vertically and horizontally away from this well, and then constrain to the overall production as well. So the bottom chart here is showing that for the well level production data, which we get on every well, we of course want to constrain our models to that. And so that tells us something about proppant transport. How is proppant being transported? What's the effective depletion length in these fractures, et cetera? And once we've established confidence in that model, we can then use it to assess things like how would that depletion profile change as we pump more or less proppant, as we change cluster spacing, as we change landing zone. How is the proppant type going to impact the depletion? So not everyone can afford to deploy 2 dedicated observation wells with tens of downhole pressure gauges to get this level of detail. But there are ways to get similar information, slightly lower fidelity, but at a much lower cost. And one of my favorite technologies or practices there is interference testing. So the concept here is with multiple multi-well development, we've likely communicated and had fractures cross between those wells. And so we can manipulate the production rate and pressure controls on each of those wells to send impulses or signals between the wells and then interpret those signals for what is the degree of connection. So very simply, you can think that if you have 2 wells that are strongly connected, right? You have, maybe if we go back to the Exxon example, right? If 2 wells were drilled at this spacing at 150 feet apart, you see that the pressure is being drawn down almost to the same pressure as the production well. So it's almost like a pipe in between the 2 wells. So if I increase the pressure on one well, I would see a very rapid and time contemporaneous response in that second well in terms of the pressure. So that's the concept of an interference test. A nice example of this is coming from Expand Energy. This was a Haynesville development. We had 3 wells in the Haynesville, slight vertical separation here. And they did a series of these interference tests where they shut in the wells and I would turn on one well and watch the pressure impulse in the other wells. And from those tests, we can interpret it, and based on the timing and the shape of that pressure derivative, we then infer what is the effective fracture conductivity that is connecting those wells. And so you get a number of measurements at different periods through time. And solid physical intuition here, we see that interpreted fracture conductivity is reducing through time. So as the effective net stress builds on those fractures, as we squeeze those fractures, as proppant embedment and proppant crushing occurs, the inferred conductivity between those wells reduces. And so that provides another point of calibration for our models, where we can say we're expecting a certain degree of connection at 50 days, 180 days, 330 days, and we need to replicate that degree of connection reduction. And then we constrain that things with like proppant embedment testing in cores, right? So we constrain as many uncertainties as we can. Then we calibrate things like proppant transport, just as in that Exxon case, to the interpreted or inferred conductivity between wells. Once again, we can arrive at these digital twin or digital representations of how this is occurring in the subsurface. I'm showing that the pressure in wells here, we see that pressure impulse where we've shut in the wells, we're producing this well, and we're watching that blue curve or blue region extend between the wells. That's the timing of the response during that interference test. The propped area is staying constant as we're not moving proppant or redilating fractures. They're mechanically closed throughout the production period, but the fracture conductivity is changing between that 50 days, 180 days, and 330 days as embedment and crushing occur. And so here we see that inferred connection between wells reducing through time. And again, provides a really robust constraint on how is this system working? How is the proppant distributed for a given design? And then what we're able to do is test that against other wells of say, is the derived interference testing and proppant transport consistent with the production data in other wells? So from that finely calibrated well pad with the 3 wells, we then tested against the 7 more wells. And what you're seeing between the actual and modeled data is highly consistent, right? That set of parameters, how we constrain the model, is consistently predictive of wells in that region. When we change things like completion design, the generation of wells, parent-child effects that Leo was talking about. And so once again, establishes yet more confidence in this model where we can use it to evaluate new frac designs, how the system is going to respond to changes in well spacing or injection volumes. All right, final realm of diagnostics that I think are really impacting modeling today and providing us with much higher detail on our constraints is on perforation measurements. So dark vision, EV cam, I think there's a number of other technologies that are actually imaging the perforations after treating these wells. So we have a pipe, we perforate the pipe, we pump the frac, then we go in and we image those perforations, and we're doing so to try to understand where did the proppant go and how uniform did we distribute that proppant across the lateral, and why this is maybe a non-trivial process is that there's two dominant physical effects that are happening in that wellbore. So if we take a gun barrel view or look down the pipe, and the perforation is indicated by this line, depending on the velocity of this fluid stream, gravitational settling is happening, right? So as we go to lower and lower rates out toward the toe of a stage, the slurry might be now moving at 5 barrels per minute instead of 90 barrels per minute where it is at the heel of a stage. At that point, gravitational settling actually starts to bias the distribution of proppant inside of the pipe. Secondly, fluid and solid particles move differently. So now if we take a profile view of that pipe, the fluid streamlines that can turn the corner or turn 90 degrees from their direction of travel and exit of perforation actually have an easier time turning that corner than a solid particle, which may slip past the perforation and continue down traveling through the pipe. And this effect, so while gravity gets, the segregation gets worse with lower velocity, the opposite is true of the slip velocity. At higher velocities, you get more proppant slipping past the perforation. So you have this complex competition between processes that are dictating the distribution. And then the final kind of effect that convolutes the interpretation here is that the erosional forcing, so what we're measuring as a diameter change in those perforations, each unit of proppant is not created equal. So the faster that piece of proppant is moving, the stronger its erosional forcing effect. And so if you just simply took a linear correlation between what the diameter of the perforation is to how much proppant went out of that perforation, you would get the wrong answer. And so that's again where we need a model to infer between the diameters to then what is the ultimate distribution of proppant. And so why would we care? why do we spend so much time thinking about these, and why are we advocating to measure the perforations? Well, the even distribution of proppant, to the extent that it's creating conductivity in these fractures, is important for ensuring the consistency and uniformity of depletion. So this image on the left is showing different uniformity indexes. you can think of a uniformity index of 1 means that every single cluster perforation received the same amount of proppant. That would be the ideal design. A uniformity index of -1 would say that all of the proppant went out one cluster and the other clusters got 0 proppant. So that's the worst case, right? So, why did you even perforate the other clusters? And so if we look at this overhead depletion view, what we see is a nice, consistent, deep blue when we're close to 1. If we model subsequent reductions in that uniformity, you see that we get more green, more patchy, which means we're leaving resource behind, and that well is not optimally depleting our reservoir. The impact of this can be on the orders of millions of dollars per well. So this is coming from the same paper as the picture on the prior slide. We're showing the financial impact of uniformity moving from that low 0.27 up to the ideal of 1 is about a $3 million increment on a per well basis in terms of MPV. This came out of some work that Hess was doing, and they were more evaluating this upper range. Right, so they already had a very good perforating design, but what they're able to show is that by measuring and optimizing their perforation designs and practices of uniformity, there's still meat on the bone where they can incrementally get more out of these wells. And so my concluding point and final point is that we can create these robust models now with these diagnostics. It's going to lead into Dr. Zhu's talk, but we can't rest on our laurels with a single optimal design. But in fact, as our commodities pricing changes, the optimal design will evolve as well. And so if we look at this chart on the right, this came out of some work in the Midland Basin or Permian Basin in Texas. And we see that the x-axis here is the optimal well spacing. Each point here is a different design, simulated design. And then I've normalized MPV on the y-axis. So at $40 oil, my optimal well spacing is kind of 2/3 through this distribution on the x-axis. As I increase the price of oil, that means I'm getting more revenue per volume, and I can actually invest more per volume of rock, right? We normally normalize on a per section basis. So how many wells am I drilling per section? Well, at higher oil pricing, I'm actually incentivized to start pushing more wells or reduce the well spacing. So if we look at this cloud of simulations, we see that that peak is actually shifting to the left as I go to higher pricing. And what I've done is I've marked that well design that was optimal at 40, and we see at 100, it's dropped off the optimal, and now I'm probably drilling half as many wells as what I should be if I'm trying to maximize the economic performance of my asset. And then this delta is about 10 or 15% in terms of the MPV extracted from that section of rock. So not on a per well basis, but on a per section basis, I am now suboptimal. And that's the importance of maintaining these models and consistently reevaluating. Is it's not a static deliverable, but instead a framework in which we can iterate through these designs and continually optimize our assets. So with that, I think I'm turning it over to Dr. Zhu.
Okay, can you see my slides? Somebody say something because I can't see the signals on the
We
screen.
do not see your slides yet.
We see you and everybody else.
Okay.
On the share button at the bottom.
Sorry about that.
Something is coming.
Now we see your screen.
And Peter.
Yeah, now I see myself. which is also nice. Here we go. Yeah, perfect. Thank you.
Okay, so continue to the first two presentation. Seems like the audience is expecting some answer to the complicated question, and I'm not sure I can provide answer, but I'm going to discuss some reality, the complexity, the problem we're trying to attack. So this is mainly just focused on using downhole fiber optic sensing technology to understand what exactly we're doing on this huge scale multi-stage fracturing in unconventional. Now, this is a very simple start point, just two sentences for those who do not know what fiber optic sensing does. Fiber optic sensing use this little fiber here, the green colored thin line. It's like a human hair diameter to measuring some phenomena in a long distance. The distance can be up to 10,000 feet, 20,000 feet, depends on the quality of fiber. When used in the field, we actually send a light signal down to the fiber, and the reflection, the backscattered signal actually bring back some information about the environment of this fiber location, which including most commonly used in our industry are temperature measurements, sometimes pressure measurements, more commonly acoustic measurement. This including the normal frequency does to detect vibration, pressure, and low frequency does to detect the string change. Okay, so on the left is the fundamental of the fiber, which is not the study focus of petroleum engineering. On the right is what we actually use in the field. So this is a typical fiber, what do we call this, waterfall plot. The vertical on each panel of this picture is the distance along the fiber, and the horizontal is the time. So this is a color counter plot. Now we recognize the pattern change based on the color change to decide what environmental parameter we're measuring is changing. So the top is the dust. The light color shows the sound pressure we observed from the fiber measurement. And this shows us the sound vibration could come out from the fluid, from some kind of pressure, casing completion, all that change. So the light color shows you receive a lot of acoustic signal, and the dark blue means there's nothing going on. Now the middle one is the temperature measurement, and this shows the cold color, the blue color means I've sensed cold temperature around me. So if I put this all together, on the vertical axis that labels where my cluster is. At each cluster location, I'm looking for the signal change. If I say the signal change, I assume I am receiving fluid, I am producing fluid. That's the fundamental. The bottom panel is the treatment record. So we're always looking for what happened in reality. Let's say I turn on the pump, I start pumping the fluid, I introduce the sand into the fluid. Each of these physical change should give me a corresponding signal change. So that's the fundamentals of this fiber technology. Now, in reality, this becomes much more complicated. Basically, there are two ways to install fiber. One is to cement the fiber outside the casing this is what we call permanent installation. And the other one is just to deploy the fiber during any time of the life of your well, just laying the fiber inside the well. Now, the bottom one is much more solid measurement. It's already there. The top one is temporary, like whenever you need this, you can deploy this. So let me just point out the cost of these two deployments is about 10 to 20 times. So this permanent cemented fiber costs about $1 million. This is like 50,000 to 100, depends on the application. For permanent fiber, when we install this in the field, and the fiber need to be protected, and the thin fiber, the higher diameter fiber, is embedded in this blue band. Now, which is clipped outside the casing. When I interpret the fiber measurement, all the hardware around the fiber should be considered. We will use the example to show how important understanding the completion strategy to when you interpret the fiber measurement. And Garrett mentioned about the permanent pressure sensor. There is a permanent pressure gauge on the right picture. So what are we measuring? Temperature. When the fluid starts moving, if you move gas, as the pressure decline, the gas expand, temperature decrease. That's just that simple. How much temperature decrease depends on the flow geometry, that is your reservoir permeability, your flow path, your completion, on, and also amount of the gas you're flowing. So measuring this temperature decline, I actually can come up with how much gas I'm producing at each location, okay, ideally. Now, water, when you flow the water through porous medium or any path, water does not expand as pressure change. Does not expand. It's expand very slightly, but there is a frictional heating. So when you produce water, oil, the liquid phase, temperature increase a little bit. This temperature increase also related to type of the fluid and amount of the fluid. So this is the fundamental of temperature sensing, try to interpret the flow rate and the fluid type distribution along a horizontal well. Now, acoustic sensing is a little more complicated from the physics point of view. You actually measuring the sound pressure vibration, and this is recorded as a sound amplitude as a function of time. And you can simply turn this to a frequency domain. So what frequency shows up in a certain time period, okay? Based on this, how much sound pressure you receive is actually also related to what you're flowing and also how much you're flowing. To interpret the acoustic measurement, the lab experiment and the CFD simulation all went up into this one very simple correlation. It says the sound pressure you received is related to the fluid flow rate to the cube, take a log. It's a linear relationship. And this has been proved from the simulation, from the live observation, and from field application. So in the dust band, we also have low frequency application. This is measuring the stream rate change as a function of location and time. Theoretically, when you start fracturing pressure, the stream water fall plot looks like this. The signal inside the fracture is since you're pushing the fracture, the rock open. This is tension. So tension is like light colored, warm colored. In the outside fracture, this is compression. It's cold color, blue colored. Now, what I'm trying to use is to identify the patterns in the field record. So whenever I see a pattern like this on the right, I know there's a fracture approaching me to the fiber wherever I installed. So this is for far field fracture hit detection. Now, application of fiber optic sensing has been used in the industry for a while, and more recently, last 10 years or so, it is like focused on fracture diagnosis and fractured well performance evaluation. So with this, we actually can do a lot. We can do fluid distribution during injection, fluid distribution during production, like all these efficiency. The first two speakers talk about 60%, 30%. I actually can use temperature to really measure the distribution of those fluid. Perforation erosion, this is what Garrett just mentioned, why this is important. We're going to use one example to look at this. Frag hit, when you see those hard shape approaching your fiber, and you know the fracture is intercepted your parent well or existing well. And the last but not the least, we really want to know the fracture system we created. We want to know the fracture geometry. And this is way beyond length, width, and height. This is the distribution of my network. If I can understand all of this, I actually can go back to optimize my fracture design. So let's see some successful or like more challenging examples in the field. The first one is a very simple fluid distribution just by temperature interpretation. So this is early time fracturing. Life is much easier, 15 stage, 4 cluster per stage. I expect 60 fractures along this horizontal well. The left picture shows the well trajectory when interpreted days. The hydrodynamic phenomena need to be considered. This is talking about the gas-liquid two-phase flow. So what I measured on the top right, showing the temperature record. This can be DTIs, or I think the first speaker mentioned several times production logging. Temperature on production logging gave me the same information. The bottom one showed the well, the bottom line on the top picture showed the well trajectory. The little triangle is your cluster. So a simple idea here, if I have a cluster that is producing gas, I should say a temperature cooling because gas expand. If at the cluster location, I don't see a temperature drop, this cluster is dead. It's not receiving or producing any fluid. By the end of the day, I come up, I would not say very simply because the computation is very heavy. You're talking about tens of hours of simulation to back match the temperature I recorded on fiber. So I come up with this flow rate distribution, which actually accidentally or correctly represent about 60% of the cluster actually actively producing fluid, 30% does not. Okay. Now the reason of this 60%, 30%, just looking at the fiber, that does not explain it. You have to go back to look at your completion, your reservoir fluid, to explain why the rest of 30% does not produce. Now, challenge in interpretation. Every time we look at a new field example, we can just get confused why this does not follow my thinking. So same well design, this is in Argentina, 15 stage 4 cluster. And we're looking at the well that's producing more liquid, just tiny little bit of gas. So based on my fundamental principle, I should say a temperature heating wherever I actually produce fluid. Now, turn out this is my temperature measurement. This is my DTS measurement. These are the measurement at a different time in the middle group of these curves. The green line on the top is my geothermal temperature. So start from the very beginning. Where is this frictional heating? Because I'm producing water and oil. If I cannot answer that question, I actually cannot interpret this temperature measurement. So it takes us a long time actually figured out. This is a production record after 3 months of production. After 3 months, the rat was still trying to recover of cold fluid injection. We have not get back to the geothermal temperature. So this gave us a hint. When I look at the temperature record, I cannot just look at the at the time temperature. We got to trace back, start from before the treatment start. What is the environmental temperature? What is the geothermal? And start from there. If we track the simulation, temperature simulation until the day we get this record 3 months after production, we actually come up with a pretty good match of the temperature, and we also come up with a fluid distribution. Now, this fluid distribution actually answered only one question: who is producing, who is not? But it still does not answer the question, why? Why this 30% of cluster not producing the fluid? So with this distribution, the last maybe 5, 7, 8 years, the industry put the effort on uniformity. Garrett mentioned that word. What does that mean? I want my green line be a straight line. I want all 60 fractures, like 60 clusters, create exactly the same fracture, produce exactly the same amount of the fluid. That's the goal of this completion design. Now the situation become much harder if I actually want to do interpretation of a current fracture design. We changed it from 15 stage, 4 cluster stage to maybe hundreds of stage, like 4 to 12 cluster per stage. So we fracture our formation much harder than before. Now, single interpretation cannot even provide the correct understanding of those today's treatment. So the next step we actually come up with is combine the measurement. This measurement could be temperature measurement, the dust measurement on sound pressure vibration, the low frequency dust on like fracture heat, on strain change, on stress field. And then we also have a downhole camera for perforation erosion. We have seismic during the microseismic during the fracturing. We have a lot of different scales method to monitor fracture. So the next example actually showed the combination of dust and DTS. They're both on the goal of fluid distribution. So just remember, these two measurements has very different physics background. Dust is to measure the pressure vibration and correlate that to the flow rate. DTS is measuring the heating or cooling because the fluid is moving in the porous medium. Example is also a simple case. This is in the Marcella gas reservoir. This is what we call M-Cell project sponsored by DOE. The left shows the field set. The right shows the two waterfall plot. Top is the dust, bottom is the DTS. Okay, and once again, I'm looking for the signals. Blue on the cold temperature on the temperature measurement shows the fluid. The warm pattern on the dust shows the fluid movement. Based on this, we did interpretation separately. This is a blindfold, 2 graduate students, they do their job. And after they interpreted the fluid distribution, they put it together. Here is the result. There are 4 clusters in one stage, and the dust and the DTS interpret very closely result, very closely agreed result on fluid distribution. So this gave us a confirmation, a proof this method of interpret fluid distribution actually works. With this, I actually have the second constraint. I'm released to further investigate another parameter. On the first step, I only know the fluid distribution. What I want to know is fracture geometry. Now this actually helped me to kind of release one constraint. Let's say if I know the fracture height, I could figure out how long the fracture is. Or if I know the height and the length, I may be able to come up with a fracture width, which to my personal opinion is the least parameter I want to know. Now with dust measurement, to actually come up with a uniformity, the design commonly used in the US unconventional development is this perforation design called limited entry. So I actually perforate less holes or smaller holes. When the fluid goes through the perforation, it actually generates a pressure drop. Because the pressure drop restricts the fluid, that forced the fluid to go to the other perforation location that was initially not receiving the fluid. The limited design actually proved that in the field, just by statistical observation, actually works. And somebody saying, I use the limited design, my production performance become better than not using limited entry design. So this actually come up with a challenge to the dust interpretation, because when you use a limited entry design, the hole start from a perfect rounded hole. Once you start pumping the fluid with sand, this hole will be eroded, become bigger really quick. When the hole become bigger, the dust signal become less significant, because this is the interpretation of your dust pressure to the flow rate is directly related to the diameter of this hole. So the student actually went in to develop a safety simulation based correlation that has the hole change, the diameter change of your perforation hole in the measurement. So the question we try to answer here is, let's say there is a lot of signal on the top right left picture saying I'm receiving fluid, but there's also one signal down here at the bottom saying I'm receiving fluid. So if you look at it carefully, the last signal coming up is right here. Looks like this cluster all of a sudden started receiving signals. So with this, if I put them all together, I interpret the fluid distribution. This picture shows the light blue are the interpretation with erosion, with perforation erosion. The dark blue is the DTS. Now you can say they start deviating from each other. What really bothers us the most is this red bars. They're the downhole camera recorder. showing the perforation area. Perforation area looks like the cluster 2 at the toe side has the largest erosion, but both DUS and the DTS could not interpret the fluid went through that. So this actually gave us a new hint. What exactly happened? You have to go back to look at this. This cluster 2 did not really receiving the fluid at a very later time of the treatment. So the fluid didn't go there until the cluster all of a sudden started opening, started taking fluid. And that is the erosion, but it's not cumulative during the injection time. That's why it doesn't have enough fluid. So those are the fluid distribution. I think, personal opinion, by far the most complicated interpretation would be the low frequency DUS frag hit. Theoretically, the idea was showing on the left. You would have this perfect, a lot of people call this heart-shaped the signal approaching your fiber. Once you hit the fiber, the fracture actually, this is on the observation well, the fracture stops there, and then the signal started changing the color. The compression become tension become compression. This is how you identify when the when the fracture is propagating to the child well, to the parent well, and the fracture actually stopped there. Now, if you look at the real life picture, that is the one on the right, you can hardly see a heart shape or cone shape or whatever the shape you want to call that. So this just by looking at the shape become a much more challenge. And I say a lot of people publish their interpretation. With your imagination, you probably can separate those signals and calling frag hit. To understand this, we actually went back to the fundamental science research. We built a lab we built a experimental setup in our lab to simulate frag hit. The experiment is very simple. I have a transparent epoxy block. I have a well drilled in the middle of the block. I bury my fibers in the block. I start pumping in the center of the well. I watch this fracture propagate out until the fracture hits the fiber that is the left panel at the second row, until the fracture passed the fiber, until the fracture reached the boundary of my block. With this perfectly controlled homogeneous situation, I actually can reproduce the theoretical prediction of string rate with stress field, the pattern. And this actually can be matched by a classical geomechanics theory perfectly. And I also can identify the frag hit location. And this also actually tells us I don't have to wait until the frag hits me. I actually can see this, the cone pattern approaching my parent well. So in reality, if you really want to stop one of those, I can see the fracture coming like maybe about 100 feet away. You actually can change your operating situation in real life to maybe lower the flow rate, maybe skip a stage. Now, this next slide is really set up to show you how complicated the real life situation can become. This is an experiment. We set up two actually fractures, try to propagate the two fractures. Everything is designed perfectly. The distance between these two fractures is maybe just 2 inches. They were designed with exactly the same geometry in this perfectly homogeneous medium. But in the reality, in the experiment when I pumped the fracture, the top fracture first received the fluid and filled up, and the bottom fracture started receiving fluid and started propagating. The top fracture never propagated, never developed. And until today, we have different opinions on why. This is not related to the heterogeneity of your injection. It's the little distance, 2 inches. The hydrodynamic actually changed the fracture propagation situation. Now, if I look at the waterfall plot, this is recorded from the experiment, you can see even the top fracture did not propagate. On the bottom panel, you can see a little shadowed area. That's your top fracture. You can see the bottom fracture propagating, but with a twisted figure. Compared with the top picture, this is a more homogeneous, symmetrical feature the classical model can predict. So with this, you know what, there are a lot of reality when I use the fiber to measure. I really did not account for it when I try to interpret the fiber measurement. This little experiment shows if I bury a fiber outside the pipe, that's my permanent fiber. I also lay a fiber inside the pipe. This is my temporary fiber. To ensure the coupling, I actually fill the pipe with gel, so the fiber was well coupled with the pipe with the fracture outside. On the right here is what I received. The inside casing fiber does not give you the same signal as outside. It's the signal was damped by the gel inside the tubing and also by the tubing. And this is the controlled ideal situation. Think about it in reality. You cement your fiber outside the casing. There's a cementing coupling to the casing. There may be air bubbles, on and on and on. So this top picture really provide a lot less information compared with what we're trying to understand the fracture. If I try to push the issue, start looking at the pattern of the top picture, I may make some wrong conclusion because of this little, like a triangle shape on the measurement. So I don't have any answer to any of the questions people posted. I just figure out in summary, we're going to say, now the measurement does have the physics hold that apply to petroleum engineer, no doubt. But the measurement has a resolution that is way, way smaller than the petroleum engineer problem. So the subsurface flow, I always tell my student, do not use decimal place. But when I use fiber, we're looking at 10 to the negative 3 to 6 scale. So how do I relate that to a subsurface phenomena? Now, the conclusion, the learning from all these years working on fiber is the following. You get a lot of different measurements. You need to cross-check the interpretation. You need to confirm this. You need to validate your interpretation. You need to calibrate your model, and then backwards use your model to get your interpretation. So there's a lot of work left to do. I still think fiber is the biggest advantage of fiber is the flexibility, the continuity, but there's a lot of work need to be done in the application for fracture control and measurement. So this is the last slide of my presentation. So I come back to you.
Thank you, Lingshu, and thank you, Garrett and Hailiu. absolutely wonderful that you have presented all your specialties. Thank you so much.